Hi everyone and welcome back to PrepFusion. I am Anish and today we will start our lecture 36 of electrical machines chapter. So today we will be discussing about speed control of DC shunt motor. So we have learned about the characteristics of DC motors. So today we will learn how to use those and how to vary the speed, because if I am connecting a load, maybe I want speed at a certain range, right? So I have to control the speed. Okay, that's why we use electrical machines. That is so that we can use our component equipment according to our own working. That is what that is the advantage of these kind of machines is, right? So we want to control user wants to control the speed. Okay, so how can I control the speed? So again, coming back to same equation, how can I control the speed? So in case of motor, we know we have a term known as back EMF. Back EMF is basically proportional to flux and the speed, right? So back EMF is proportional to the flux across the motor and the speed. So back EMF EB is equals to Km phi n, and my back EMF is also equals to Vt minus Ia Ra, right? So from here what we can do, like we can vary our, so what is our speed dependent on? Our speed is basically dependent on Eb upon Km into phi, or I can directly write my speed is dependent on Vt minus Ia Ra divided by Km phi. Okay, so what things can I vary? So generally, right? Obviously, I cannot vary that supply voltage. Supply voltage is not allowed to vary. So if I want to vary my speed, so I have the option of changing my flux. How will I change the flux? By connecting an external resistance with the shunt winding. Okay, by connecting a rheostat with the shunt winding, or I can vary the Ra. If I vary the Ra, then this drop will be varied. Then of course, Eb will be changed. Then of course the speed also will change. Ia may not change because Ia is dependent on the load torque. So there are many ways to control. So first method of control, which is the most used method, is known as the field flux control, where we will control the flux of the field by connecting an extra rheostat. Why? How? Because I know the shunt current or the field current is V upon RSH, and if RSH is varied, then the field current also will be varied. Although the winding resistance is same, but I will connect an external resistance R external that will vary. Okay. Now, uh, what is the second one? Second one is the armature resistance speed control. Armature resistance speed control. Okay, so basically here we connect a external resistance with the armature, and the third one is the armature voltage speed control, where we will control the voltage across the armature directly. Without controlling the drop, I will directly control the armature voltage. So the third one is the armature voltage speed control. Okay, so these are the three different methods of speed control. Now one more thing, key terms that I want to explain over here is that we have two kinds of torque. One is the developed torque and another one is the load torque, TD and TL. So what is TD? TD is known as the developed torque, that is the torque developed by the motor. And what is TL? TL is the load torque that is the torque that the load wants. Okay, and already we have discussed this, right? What have we discussed? That in steady state, when the load torque will be equals to developed torque, the machine will rotate in constant speed, right? So this happens in steady state condition. Steady state condition. This happens in steady state condition. So here there is constant speed. Steady state meaning speed will be constant here. How is speed constant? So very basic, if I remember the linear equations, right? So my acceleration was equals to dv upon dt, correct? So if there is zero acceleration, that means what does zero acceleration means? You know what is force equals to? Force equals to mass into acceleration. So okay, I'm running out of pages, so let me take it in the next page. So there will be one, like if this box is there, okay, there is one force I'm applying here, applied force, and there is one restoring force, right? Now if F applied equals to magnitude of F applied equals to magnitude of F restored, because they are acting in opposite direction, magnitude are same. So overall force here is 0, right? Force equals to mass into acceleration. Mass is just a constant number, so acceleration is 0. So if acceleration is 0, that means my dv upon dt is 0. Now if I integrate on both sides, my v becomes a constant number, v equals to c. So it is constant. You can apply the same principle for rotational motions. Okay, in case of rotational motions, instead of force you will replace with torque, instead of acceleration you replace with angular acceleration, that is alpha, instead of what do you call, instead of your speed you will replace with angular speed, omega. So in steady state condition, omega will be constant, omega m. Now if it is the other way around, if the developed torque is greater than the load torque, that means there is one restoring force here, but the applied force is higher, what will happen? This block will accelerate. This block will accelerate because now my force acceleration will not be 0 anymore, F net. This is F net, right? F net. Now the force is not 0 anymore, hence the block will simply accelerate. Okay, so here the block will simply accelerate. Okay, acceleration will happen. Okay, divided by, so this here, right, omega m will increase. And in the last condition, if let's say my developed torque is less than load torque, then there will be deceleration. As the name says, right, restoring force is higher than the applied force, of course the block will go backwards, so there is deceleration. So whatever the speed initially it was, if it was initially going here with a speed of c, right, as the opposing force is higher, so it will, now the speed will reduce. After a certain point speed will go negative, that is it will move in the opposite direction, right? Deceleration, deacceleration. Okay, so my omega m reduces. So these are the main key points that we have to understand. So now we will actually basically solve finally. So here, right, whatever we have discussed, speed depends on this, n equals to e upon k phi. So we can control by, okay, not by adjusting the terminal voltage, no, by changing the flux, by yeah, by adjusting the armature, not armature terminal voltage, by adjusting the armature voltage. So although it is directly the terminal voltage only, but let's not say it like that. Let me say only the armature voltage. Okay, one more thing I forgot to mention, that in the previous lecture, right? Okay, now I just remember because I am deleting this. In the previous lecture, I told you one thing. It's a very huge like blunder from my end. That, yeah, in the previous lecture that page was also open. That's why I forgot. So in the previous lecture, I discussed about series starting torque of series motor, right? Just a mistake on my behalf. I told that series motor does not have high starting torque. That was a mistake on my behalf. Okay, series motor actually have very good high starting torque. Okay, here. So what is, yeah, here, right? In the previous lecture I actually just deleted this. Why it has the high starting torque? Because initially what will happen? Initially the motor is not rotating, so speed is zero, so flux is zero, so the IA current will be huge, starting current is huge. If starting current is huge, that means the torque also will be very high. Torque is phi into IA. Now phi is some constant value, there is some residual flux because initial flux is zero, so initial starting current will be very high, so that's why it will produce very high starting torque. Okay, just a mistake on my behalf. So that, yeah, so that's why they are ideal for these traction systems, elevators and electrical trains. Okay, yeah, I hope you have understood this basic point. Okay, because what happens is, one thing is there, right? Initially in case of shunt machine, you might say, sir, in shunt machine also the armature current will be initially very high. Yes, you are correct. In shunt machine also the armature current will be very high, but what was the difference? In shunt machine, the torque for a shunt machine, the torque was proportional to flux IA. And I know in case of shunt machine the flux is constant, right, because the IF current is constant. So torque is proportional to IA only. In case of series machines, torque is proportional to flux IA, which is proportional to IA whole square, correct? Because flux is also same as IA only, because same current is flowing through the field windings. So it is proportional to IA whole square, and this is proportional to IA only. So of course, which one will be higher? IA whole square. That's why the starting torque of series motor will be much higher than the shunt motor. Okay, so I hope that is clear. I'm sorry for the confusion. I hope माफ कर दिया होगा आप लोगों ने. तो yeah, then let's start here. So yeah, we will adjust the armature voltage by varying the armature resistance or by changing the field flux, which in turns we can vary the like shunt resistance, right? So we are discussing about shunt motors today. So one more formula, basic formula you already know, that my speed in radian per second omega m will be 2 pi n by 60. So if they are asking you to find out in radian per second, then you will write this omega m equals to 2 pi n by 60. Now again, speed regulation, I had discussed this previously as well, that there are few important terms that we should keep in mind when we were discussing about speed control. First one is the base speed. So the rated speed of the motor as specified in the nameplate is known as the base speed. That means if I apply a rated terminal voltage at rated flux at normal operating condition, what is the speed of the machine? So that is known as the base speed. Okay. Now what is speed regulation? Speed regulation, same as voltage regulation. It is the drop from no load speed to full load condition. Ideally, a good motor should have low speed regulation similar to a voltage regulation in case of generator. Okay. So of course, initially if the motor was not driving any load, it will rotate at a very good speed. Once I will connect a load, the load will provide a opposing torque, right? So now the speed will reduce because it will decelerate. Okay. So this is the formula for speed regulation. And what is the speed range? Speed range is the range between minimum and maximum allowable speeds. Speed range is the range between minimum and maximum allowable speed. Okay, that is what the speed range is equals to. Okay, so it is omega max minus omega min. So these are the three terms that you must know and understand. Now there are few more terms related to electrical drive. So this, when you will study drives, there we use this term, but here I have to explain only the two terms. First one is the constant torque drive, third one is the constant power drive. So I know this formula, right? Like EB into IA, the developed power, is equals to omega into torque, mechanical power here, and this is the developed electrical power, correct? So what I can say, EB into IA is basically the power output of the DC motor electrically, right? So if it's a constant torque drive, that means the torque will be constant. Okay, that means if I increase my speed, power will also increase linearly. So in the first one, power varies linearly with speed if the torque is set to be constant. If it's a constant power drive, then this value is constant, then torque will be inversely proportional to speed, or speed will be inversely proportional to torque. Okay, so power remains constant across varying speed. If I vary the speed, power will be constant, that means the torque will be inversely proportional to the speed. So if speed increases, torque will reduce, that's it. So that's why here torque is inversely proportional to speed. Okay, that's basically it. Okay, so yeah, I hope we have understood this basic point. Let's now discuss about the first one, that is the field flux control, right? In field flux control, what do you do? Very simple and easy to understand. We will just connect a external resistance, and by varying, so what is my IF or IF current? So my IF current will be equals to Vs by RF plus R external. Okay, so IF current is Vs divided by RF plus R external. So if I will vary my RF, of course the IF current will vary. So here, right, what is the important factor here? So important factor is, if, like, what is the range of R external? Of course it's a passive device, so R external minimum value can go to 0 to some R max, right? So what I am observing, so when R external is 0, that means my IF will be Vs upon RF, and this flux is actually, this current is known as the rated field current at rated condition, right? After this, if I keep on increasing my R external, the IF current will just keep on reducing. so the flux also keeps on reducing. So I can only, there is a limitation to it. I can only reduce the flux, I cannot increase the flux. That is a limitation. So if I can only reduce the flux, so this portion is constant, right? So what is changing? So speed is inversely proportional to flux. So if I can only reduce the flux, the speed can only go upwards. I cannot go downwards. And when my IF is rated, then my speed also will be rated. And from rated speed, I am only going upwards. So what is rated speed? Rated speed is known as the base speed, right? Rated speed is known as the base speed. So I can only go upwards from the base speed. I can only go above the base speed. I cannot go below the base speed. So here, if I see, used for speed above the base speed, because I cannot control it below the rated speed. Okay, I cannot bring the flux to a higher value. I can only lower the value of flux. So that is the disadvantage of this method. Okay, you can understand this with the torque equation as well. Okay, how can I understand this with torque equation? So you are saying that you are controlling the speed here, right? So what is happening to the torque here? What is happening to the torque? So if I see speed is, if I see speed is increasing, okay, what is happening to torque? So torque, if you see, torque, developed torque is proportional to flux into Ia. Now if torque is proportional to flux into Ia, you are saying that you are reducing the flux, so your developed torque should reduce, right? And if your developed torque is reducing, that means what? There is deceleration. But you are saying there is acceleration because speed is increasing. How is it possible? So basically what is happening, one more formula there is the developed EMF, right? So what is the developed EMF? So developed EMF is proportional to phi ZNB or phi n, right? So for a second, if I assume speed just for a second, if it remains constant, then what happens? The flux is reducing. So if flux is reducing, the EB is reducing. So what will be the IA value? IA was, if you remember, Vt minus EB by RA. So if EB reduces, the overall IA will increase. So this will increase more further. So basically in these cases, what will happen? The increment. So basically, let me color this with different color. Increment in IA will be greater than the decrement in flux. Hence, overall torque, developed torque will increase. So my overall net torque is equals to TD minus T load. Load torque is fixed. So TD is increasing. Hence, overall this is increasing. Hence, there will be acceleration. That's why overall the speed will increase. Okay, now if the speed increases, what happens? It's like a feedback. If the speed increases, the EB also tries to increase again. If EB increases, what it will do? It will try to neutralize the armature current. So if EB increases, the armature current again will try to reduce. So it will neutralize the armature current. Okay, that is what happens. So initially, for a second, the torque increases. Then again, as torque increases, there is acceleration. If there is acceleration, speed increases. If speed increases, EB increases. If EB increases, IA goes down. If IA goes down, the torque goes down. So the acceleration is also reducing until it reaches a steady state value, that is TD equals to TL. So acceleration will reduce. So what happens? There is acceleration. So acceleration, the acceleration will reduce until it reaches steady state value. Okay, got it. So yeah, when TD will be equal to TL, then the speed will be simply constant, but speed will increase slightly. Okay, so that is the overall phenomena. A variable resistance is added in series to further reduce the flux. It is also known as field weakening method because the field flux is getting weakened. Smooth and simple method to controlling the speed above the rated value. Efficient as field current is typically low, so copper losses will be very low in the external resistance. So because there will be some, if I am adding a resistance, there will be some copper loss in the external resistance, but as the field current is so low, so it does not matter. Okay. Disadvantages, as I mentioned previously, not suitable for speed control below the base speed. During transient increase in armature current can cause stronger armature reaction, because initially, right, there will be bit increasing in armature current as I discussed, right. So if in transient the armature current increases, there will be stronger armature reaction, distortion in the main field, poor computation, and sparking can also occur at the brushes. Okay, so these are suitable for lathes, spindles, paper machines where the speed is generally higher than the rated speed. We operate it at higher than the rated speed. Okay, so generally used in high speed operations for brief periods. We cannot use high speed for larger periods because the armature current will increase very high and that can cause a bit of issues. Okay, so flux should not be reduced below safe limits, may cause the armature to overheat because the current will be very high. Current will go very high, and if IA goes very high, there can be huge copper losses. Increase current for same torque, instability due to armature reaction. Current goes high, armature reaction also is very high. Okay, so these are the drawbacks and features of field control. Now let's discuss about armature resistance control. So this is the circuit for armature resistance. Okay, let me bring it. So very, it's like same thing only, that right now what will be my, basically, what do you call, what will be my because I am controlling the current now, or the EB. Okay, so what is my EB? So my speed, right, is equals to 1 by Km into Vt minus IARA divided by flux. Okay, so of course this is constant. This is constant. We are not changing the flux here. What we are doing, we have added a additional R external here. So the IARA drop has become IARA plus R external. Okay, so this drop has now increased, right? This drop has now increased. If this drop has increased, overall my EB will reduce. If EB reduces, what happens? The speed reduces. So here, right, one thing I observe, if there is no R external, then the speed is basically directly proportional to Vt minus IARA, right? That is it is the rated speed. Rated speed. Now if R external is present, not equal to 0, it is greater than 0, then what happens? Then this, right, becomes Vt minus additional subtraction is there, Ra plus R external. Hence this reduces further, hence the speed reduces further. Can I increase the speed? No, I cannot increase the speed. Speed cannot be increased in this case. So I can only go below the base speed. That is what here is written over here, used to control below the base speed. That's why it is written over. I can only control below the base speed because I can only go below the rated speed. I cannot go above the rated speed. Okay, now here also what is happening in transient. So initially if I connect a R external, what happens? There is a bit of drop. Due to the drop, speed reduces, right? So what about the torque? What is happening with the torque? Torque is proportional to flux into Ia. Now what is Ia is equals to? Ia is equals to Vt minus Eb divided by Ra plus R external, obviously. So if at an instant, if I connect the R external, if I keep on increasing the R external, the Ia reduces. If the Ia reduces, the developed torque reduces. So if the developed torque reduces, that means what? What is my net torque? Net torque is Td minus T developed. So developed torque reduces, so net torque also goes down. That means what? It is decelerating. There is deceleration. Deceleration, right? Deacceleration. If there is deacceleration, that means what happens? The speed is reducing. If speed reduces, what happens? The back EMF will reduce. If back EMF reduces, this term will reduce. If this term reduces, this overall thing will increase. If this increases, overall Ia will increase. If this increases, Ia increases, again the torque will increase. So initially the torque will reduce, it will decelerate. So the armature current reduces. So there is no problem of armature reaction here. So I can write here as armature current reduces, no problem, armature reaction. Okay, so that is the advantage over here. Now let's discuss about this method, right? So an external resistance is connected in series with armature, simple and easy to implement. Armature current decreases during control, reducing the risk of commutation issues because the armature reaction is lower. Not usable for speeds above base speed. Of course, that is a disadvantage. We cannot use it above base speeds because the uh, because EB will always reduce. It cannot increase. Okay, high armature current causes significant copper loss in the added resistance. So previously, right, there was field current. So previously the loss was basically the loss was IF whole square into R external. Now IF itself is very small, so the copper loss is very small. But here the problem is the copper loss is IA whole square into R external. So the copper loss is IA whole square into R external. So that is a problem here. That is a problem over here because it is IA whole square into R external. IA itself is a very large current, so the copper loss will be higher. So efficiency will drop significantly because the current, right, the loss in the current will be very higher. Okay, that is the only disadvantage in this case. So okay, this is already written over here. Okay, that is already present. So the applications, I can see applications. Cranes hoist small mechanical drives with low speed operation. Where low speed operation is required, like cranes and hoist, there we use this. Speed drops significantly under load due to voltage drop across the resistance. Simple but inefficient, energy is wasted as heat. Poor speed regulation, not suitable for precise speed control because speed regulation is very bad in this case because speed drops very highly at low speeds, right? Okay, so now let's discuss about the third one, that is armature voltage control. So armature voltage control is nothing, like I will not explain here further much. Okay, it is nothing but just connecting external power electronic devices, electronic circuit that will directly control the voltage of the armature. Okay, so let's say it is a DC to DC converter or DC to DC chopper. So generally we use a DC to DC chopper. So only advantage is energy will not be wasted in the R external, right? Here we are not connecting a external resistance. We are connecting a chopper, power electronic device that will control the voltage. Remember, we cannot go beyond the rated voltage of the armature. So I cannot increase the voltage across the armature. So I can only decrease the voltage across the armature. That means EB will only go down. If EB only goes down, speed also only goes down. That's why this method of control is known as the base speed control. Okay. So whatever, same analysis as the previous one, same analysis as previous one without R external. Okay, without R external. So technique, varying the terminal voltage VA of the armature using an external source like a chopper or control rectifier while keeping field current constant. So field current will be of course constant here. We'll make the field current constant. Just a remember, this terminal voltage will be constant. We'll connect a DC to DC chopper that will just control the armature voltage. That will not control the terminal voltage. Terminal voltage still will be control, right? So ultimately, actually, one mistake I have made. This will not be directly connected. So yeah, one mistake I have made. This right will not be directly connected. Actually, the converter will be connected to the supply and the converter output will be given, the chopper output will be given to the armature. So the chopper will actually, okay, this is not, so the converter is connected across the supply. Okay, and this output of the converter is controlled. Okay, and that is provided to the machine. So that is the advantage. So actually we don't connect the external resistance, we directly give the output of the converter to the DC machine and that is controlling. So here the input of the controller is Vs and output of the converter is some voltage, right? Whatever voltage we want to control. So this is the highly efficient because there are no extra losses because external resistance is not added, provides fine and smooth speed control and it maintains the rated torque across wide speed range. So this is actually very good method to use, but the problem is we need extra expensive power electronics like chopper and converters. Those are expensive devices. So where efficiency is very high criteria, so cost will go up for the machine for the external circuitry, but at least the energy will not be wasted much. So we will be saving in energy. So in those kind of situations, this is used. So cannot be used to increase the speed beyond the base value may damage the insulation because I cannot increase the voltage across the armature, because if I increase the voltage across the armature, what will happen? It can damage the insulation as it has said over here, right? So it is used in industrial automation, CNC machines, battery powered electric vehicles. So our latest vehicles also use these kind of choppers to basically improve the speed. Okay, so now let's discuss about the torque speed characteristics. So if I see in case of uh, so about torque speed and power characteristics, if I want to discuss, so let us discuss about torque torque, speed and power characteristics. So first one we discussed was the field flux control. So in field flux control, what did we control? We controlled the flux, right? Flux was reducing. Okay, we controlled the flux. So if flux was reducing, my speed was simply increasing, right? That is what we controlled. So what is the power? Power is basically EB into IA. So we don't change the armature current. Okay, we don't change the armature current, right? So what is EB? EB is basically some km phi into speed into IA. So armature current is assumed to be constant. So what we do, we reduce the flux, but the speed increases. So overall what happens is the power remains constant. So for a field flux control, the power is actually constant. So if I draw the power speed graph, the power will be constant. Power will be basically constant. With varying speed, if the speed increases, what happens? The flux further reduces, so the power is still constant. So it will just be a constant line like this. So this is the constant power line with varying speed. What about now? Remember, this is the rated speed, because I can only go above the base value, I cannot go below the base value. So let's assume this as n rated. The speed can only go above the rated speed, I cannot go below the rated speed. Okay, what is happening to the torque? So what is the torque equation? So the torque equation is kt phi into ia, and if I assume my ia to be constant, then my phi is reducing, so torque is actually reducing. Okay, so torque is actually reducing, so torque graph will be somewhat like this for a field flux control. Okay, so what kind of drive it is? It is a constant power drive, because here the power is constant. So for a field flux control, it is a constant power drive. Okay, it is a constant power drive. Now let's do the second one, the armature resistance control and armature voltage control. Both are the same only, because ultimately we are controlling the armature voltage. I am not discussing about the efficiency here. This power, right, is the power output at the motor. Okay, you might ask that in the external radiations there will be some power loss, so the term whatever power I am sending from the supply, that is not constant. Yes, you are correct, but I am discussing as the power output at the motor, that is EB into IA. This is the power output at the motor, okay, not from the supply. So armature resistance control and armature voltage control. Okay, armature resistance control and armature voltage control. In this case, what do we control? We control the EB gain, but this time the EB is made to go down. If EB is made to go down, what is my speed? Speed is proportional to EB upon flux. Flux is constant, so speed will go down. Okay, so here the graph will be below the rated speed. So this is my speed, this is my power, and this is my basically torque. Okay, so I see that the, like, if this is my end rated, I will only discuss about the below the rated speed. So in this case, what happens is that so EB is reducing. So basically, if I see, if power is equals to EB into IA, so EB reduces. If I assume my IA to be constant, then power also will reduce. So here actually the power is not constant anymore. Power will be reducing, same as the previous case as the torque. So power will be reducing. Okay, so let me draw it with yellow. Power will be reducing. What about the torque? So the torque, if I draw in green, so torque is basically KT phi into IA. So flux I am not changing. What about the armature current? So previously, right, what was happening is that okay, yeah, both are constant. Flux is also not changing, current is also not changing, so torque will be constant. So in this case, the torque will be, sorry, not after, before, right, sorry, whatever it is before this. So here, right, what is happening, my power is directly proportional to EB because current is not changing, so it is linearly proportional. So the, what will happen, basically the power will be like this because it is below the rated speed, right? It will be somewhat like this. I'm linearly reducing my armature voltage with chopper, right? I'm linearly reducing my armature voltage with chopper, so it will be a linear relation. For power, for torque, it is constant because IA is also not changing and flux is also not changing, so it will be just a constant torque drive. So torque will be constant, it will not vary with respect to speed, right? So with respect to speed, if I reduce my N rated, what happens? My EB reduces. If EB reduces, my power will reduce. Okay. But if I reduce my speed, right, torque is constant because phi and IA will be constant. So in case of armature voltage and armature resistance control, it behaves as a constant torque drive. Okay, that is the difference basically. So what we do, actually what we do, we combine these two graphs together to make a single. So for controlling above base speed, we will use field flux control. For controlling below base speed, we will use torque, sorry, we will use armature voltage control. So this is above base speed, and this is below base speed. Okay. So yeah, the whole graph will be like, I will copy the whole graph. I will copy this one. Make it bigger, paste it over here. So what we do is basically we combine the two graphs. Okay, that is our main objective. We combine the two graphs and we use it for our speed control. So this will be above base speed, and below it the power will be constant. Okay, let me bring it further down. And the torque will be, sorry, power will be linearly varying and the torque will be constant. This one is the below base speed. So this portion is the flux control this portion is the armature voltage control. Okay, so I hope you have understood this point. So yeah, that's the case basically. So the advantage, if I see, I will combine. So armature voltage control is used for below base speed. Field flux is used for above base speed. Omega will be less than omega base, constant torque region. Omega will be greater than omega base, constant power region for speed. So advantage, wide and smooth speed regulation. So we will combine both of these methods together. So it will provide good speed regulation, easy reversal of rotation. Higher efficiency at low speed compared to resistive method. So low speed we can use the armature voltage control, that is the that what do you call, the third one, right? Third one, not armature resistance voltage, armature resistance control. Easy reversal of rotation. So if I want to reverse the rotation of the generator, like if I want to reverse the rotation of the motor, what can I do? What can I do? I can simply rotate the field terminals, right? This we have learned in the previous lecture. So that is why it is known as easy rotation of the generator. But the drawbacks, like what I am doing, I'm combining both the methods, that is dual control. It is known as dual control, where I'm combining both the field flux control for above base speed and armature voltage control for lower base speed. But the disadvantage is, of course, it will become more bulky and expensive because I'm implementing more stuff inside the machine, requires more space, and maintenance cost also will go higher. Of course, expensive because I have to do the field flux control as well as the armature voltage control. Okay, so these are basically the comparison table. You can go through this. Okay, now let's do few questions. So yeah, you can try these questions out. Please pause the video and try these questions out, and then I will solve all these questions. Okay, so these are the okay, this is the last question, I guess. Oh, okay, we have a lot of questions. Okay, we have a lot of questions. Okay, so yeah, let's start with this one. Yeah, let's start with this one. So if I observe that a separately excited DC motor has an armature resistance RA to be equals to 0.05 ohms, the field excitation is kept constant, so flux is constant at an armature voltage VA 100 volt. The motor produces a torque of 500. So this is VA1, T1 is equals to 500 Newton meter at zero speed. So there is no speed right now. Okay, so n is 0. Okay, how is n 0? So assuming initially 0 speed, of course it will accelerate. Neglecting all mechanical losses at no load, speed of the motor for armature voltage equals to 150. No load, what will be the speed of the motor at a armature voltage of 150? That is what they are asking. Okay, so first of all, flux is constant, so how much will the torque increase? So torque, right, it is operating at no load. If it is operating at no load, right, if it is operating at no load, okay, that means initially it will have zero speed initially, and initial will be equals to 0. That means my EB voltage will be equals to 0. So what is the current? IA current will be equals to what? IA current will be equals to uh, it will be it will be VA minus, so VA2, IA2 will be VA2 minus EB by RA, right, and EB is basically 0, so it will be VA2 by RA. VA2 is 150, 150 by 0.05, so it is 1 by 10, 1 by 2, 1 by 2, 1 by 20, so 3000 amperes, which is huge amount of current. Okay, which is huge amount of current. It will take huge amount of current, right? Now in the case 1, what is the current it is taking? IA1, again, if the speed is in force, of course you will say how is the speed 0 if there is some torque, right? So assumption is that what we do is, initially we are talking about the initial speed, so this is the initial current. Okay, after that of course the speed will increase, so the torque, I mean the this IA current also will reduce. So IA1 is equals to VA1 minus EB divided by RA. So again assumption is N initial is 0, so this will be 0, so developed voltage will be 0, so it will be VA1 divided by RA, so 100 divided by RA is 0.05, this will be 2000, like huge current. Can you observe how much huge current is flowing? 2000 amperes. What is my torque? Torque is proportional to flux into IA. Now they have told me already that flux is constant, no matter what, flux is constant, so T1 divided by T2, T1 divided by T2 will be equals to IA1 divided by IA2, right? This is what I know. So from here, what can I, okay, this is already I know, right? IA1, IA2, yeah, IA1, IA2 already know. Second, okay, second, yeah, T2, okay, T2 I don't know, so I can find out the torque in the second case. So T2 torque will be what? T2 will be equals to, this T1 is 500 into IA2, IA2 is 3000 divided by 2000, so it will be 3 by 2, so 250 into 3, 750 Newton meter. So now the torque is 750 Newton meter. So now let's discuss about a fundamental thing, that is this equation, EB into IA equals to omega m into torque. Okay, so what do I know? That my torque is proportional to flux into IA, correct? So torque is equals to, let's say some kT phi into IA. What about EB? EB we know is proportional to flux and speed, right? N or omega, whatever you write, it does not matter. Okay, well, let me write it omega only, because omega is proportional to revolutions per minute, that does not changes here. Okay, so the EMF is proportional to this. So here what I can write is that my E, let's say, is equals to some Ke phi omega m, because yeah, speed is like E is phi ZNP by 60, so E will be proportional to phi omega m. So I will replace here, okay, because I want to come to a fundamental conclusion. So if I replace here EB, that is Ke phi omega m into IA, and if I replace on the right hand side, omega m will be omega m only, torque will be replaced with Kt into phi into Ia. So what do I see? Omega m is cancelling out, omega m is cancelling out, Ia is cancelling out, Ia is cancelling out. Okay, now I can cancel them out only if they are not 0. Okay, then only I can cancel them out. So flux is cancelling out, omega m, Ia, omega m, flux cancel out. So basically what do I see? That I see that the Ke constant, Ke is equals to Kt. right? This always holds. So basically the main important factor is this constant and this constant, both of them will be same. Okay, if I assume it to be proportional to omega m. So this is the property that I will use basically. This is the property that I will use. So in the first case, right, in the case 1, like there is a mistake in here, I will discuss about that, don't worry. So in the case 1, this was my torque. So I can write my torque T1 as Kt into phi into IA1, and I had already find out my IA1 current. IA1 current was 2000 amperes. So from here, right, I can directly find out what is Kt into phi, because Kt phi will not change because it is a shunt generator. Terminal voltage will not change, so Kt phi will not change. So this will be T1 torque in the first case was 500 Newton meter divided by this current, that is 2000, correct? So this was 0.25, whatever is the unit here. Okay, I'm not writing the unit over here, whatever is the unit. So this we will use in the second case. Now in the second case, they're telling it is operating in no load. Okay, and ignore the mechanical losses. So if it is operating in no load, right, in the case 2, if it is operating in no load, so actually no load means it will not take up any armature current. So IA2 will be equals to 0 at steady state. Initially it will take up some current, but as it is operating in no load, so armature will not take up any current. This analysis whatever I was doing was for the initial state, but as it is operating in steady state, so it will not take up any current. That basically means that it is operating in no load, just like a generator, right? If I say generator is like there is no load connected to the generator, what do you say? There is no load current, right? IL equals to 0. Same thing. If the motor is not loaded, that means the armature current is 0. So if the armature current is 0, that means what is my armature voltage? EB is equals to VT minus IARA, right? So IARA is 0. Basically armature voltage is directly equals to the terminal voltage, and they have already told me what is the voltage across the armature in no load, that is 150 volts. Armature voltage is 150 volts. So it is 150 volts. So this is what my EB is equals to. Okay, this is what my EB is equals to. So this will be equals to what? Ke into phi into omega m. So I know Kt into phi, which will be equals to Ke into phi. So from here I can directly say that omega m will be equals to 150 divided by 0.25, that is 600 radian per second. Okay, but there is a bit of mistake here, because if you are assuming your armature current to be 0, then you cannot simply cancel this out, because I cannot cancel if like something is equal to 0, right? I cannot cancel things out. I hope you know this, right? So but even when armature current is 0, anyways this will satisfy. So you assume that armature current is very low value, small value, very small value, that even if it is operating in no load, of course very small value is there, then you can cancel this equation out. Then you can directly say that your Ke will be equals to Kt. Okay, that is the only thing that you have to understand. So here the answer will be 600 radian per second. Okay, 600 will be the answer. Let's now move on to the next one. A 240 volt DC shunt motor has a armature resistance Ra of 0.5 ohms, and it draws a current Ia of 40 amperes at full load. So this is the Ia full load. Okay, it draws a current of 40 ampere full load. So actually it will be the Ia full load is 40 amperes. And what are they telling? They're telling me that if an external resistance R external is connected 1 ohm in series with the armature, Determine the ratio of the starting, that is stalling torque, to the full load torque. Okay, starting means what? In case of starting, when we are starting, right, what is the condition for starting? Starting basically means that the speed, initially the motor is just starting, that means the speed is 0. That means if speed is 0, that means the back EMF will be 0, right? That means what will be the current in starting? I starting will be simply equals to the voltage Vt upon Ra plus R external, because there is no back EMF, correct? So this will be equals to Vt is 240, Ra is 0.5 plus R external, that is 1, so 1.5. So it is 3 by 2, so 18 into 2, 160. 160 amperes will be the starting current. Okay. Now how do I determine, like what are they asking? They are just asking the ratio. So how do I find? So what is torque proportional to? Same thing, right? Torque is proportional to phi Ia. In case of shunt, this is constant. So I can directly say that torque will be proportional to Ia. So the ratio of starting, also known as the stalling torque, okay, ratio of starting torque over the full load torque. This will be equals to the I starting divided by the I full load. So what will be the full load current? Full load current, they have already told me, is 40 amperes. So at full load it will take 40 amperes no matter what, right? Very simple. So this question was very simple. So this will be initial starting current was 160 divided by 40. So this will be 4. So 4 will be the answer for this particular question. Okay. So let's now do the next question. A 440 volt DC shunt motor operates at no load speed of 2000 rpm with armature current equals to 0. So at no load means armature current is 0. The terminal voltage is 440 volts, operates no load, n naught is equals to 2000 rpm. If at full load and reduced armature voltage while maintaining full excitation, n full load is 1000 rpm, where the current is Ia full load. When the load is halved, that means Ia dash is IAFL divided by 2. If the load is halved and the armature voltage remains unchanged, so VA dash is equals to the previous armature voltage VA, so the EB also will not change, right? Then the speed rises, N dash becomes, speed rises to 1050 rpm. Determine the armature voltage drop at full load assuming armature reaction is negligible. So basically they are asking me what is the armature voltage drop. Okay, so how do I find out the armature voltage drop? Okay, so initially, okay, let me just write down the cases over here. Let me write down 3 cases. So this one was the first case, this one was the second case, and this one was the third case. So in the first case, my, like, of course voltage will not change, okay, or in the first case Vt is 440 volt, operates at no load. So if it operates at no load, right, the armature voltage also will be same, V also will be 440 volts, because there will not be any drop in the armature. So in the first case VA will be 440 volts, the speed will be 2000 and naught will be 2000. RPM, and your IA naught will be 0 because it is operating at no load. Okay, so what will be your, like, back EMF is same, this EB naught, right? No load voltage will be same as this terminal voltage, that is VA naught. Why? Because it is VT minus IA naught RA, and IA naught is 0, so that's why it will be equals to VT only. So your EB naught So your EB naught will be equals to 440 volts. Okay. Now again we will try to find out the constant. So what is the constant? Constant is, I know my Ke phi omega m is equals to 440. So from here I can directly find out what will be the Ke phi omega. Now one thing I will do, instead of I am writing in omega, right, everything is mentioned in revolutions per minute, so I will write this value. I can change, because that will, if I change here Ke phi n, just this constant will change, that's it, because omega and the revolutions per minute are dependent to each other by a constant factor. So just this constant will change, that will not make any difference. So I can directly say, from here I can directly find out the this Ke phi value. So Ke phi will be 440 divided by 2000. So I got my Ke by phi value. Now in the second case, they have not mentioned what is the armature voltage at full load. They have not mentioned that. Okay. So I don't know what is my VA dash. I know what is the full load IFL. I know the full load speed. If I know the full load speed, will I be able to find out the armature voltage? Definitely yes. Yes, right? Because my EB, right? My EB is proportional to, basically EB is proportional to flux and speed. So EB naught by EVFL will be equals to N naught divided by NFL, because the flux does not change. So this will, what will happen? My EBFL will simply be EB naught, that is 440 into NFL. NFL is N full load, they have given me as 1000 divided by 2000. So this will be 220 volts. This will be 220 volts. Okay. Now how do I find out the drop over here? So from here I can, what I can say, I know my EBFL will be equals to VT minus IA FL into RA. So from here I can directly comment what will be the drop here. So the drop here, IAFL into RA will be VT minus EB RA, that is 220 volts. So here, right, very key point, one key point we have to understand. So if I draw the circuit, so actually there are a few voltages that I want to explain you. So few things that I want to explain. So in case of armature resistance and armature voltage control, right, the voltage actually is changed. So the supply voltage and the voltage across the terminals are not same anymore. What do I mean by it? So this is the voltage across the supply. Now this is my voltage across the armature, because there is an additional voltage drop across the RXT. So what will be the drop? Here the drop will be IARA into RXT. RXT value they have not given to me, so I don't know this. So that's why the voltage across the armature is this. Okay, and the back EMF voltage is this. So there are many things here. There are 3 voltages now. Previously there were only 2 voltages. So this VA and VS both were same previously, but now they're different, because as I'm connecting an external resistance, so the voltages are changed. Okay, so here what I will say, is that here, right, this VA and VT, the terminal voltage, both were same in the first case, because it was at on no load. If it is at no load, there is no drop here, zero drop, right? That's why the drop across IA naught into RXT was 0. That's why it was directly equals to my EB. Okay, that's why. Okay, I hope that is now clear. Now In the second case, the armature voltage has changed. I don't know, they have not mentioned me the armature voltage, but I know the back EMF because I knew the back EMF previously. Back EMF will be proportional to the speed. So in the, so this equation is actually not correct, right? This equation will be, armature voltage will be, back EMF will be VA dash minus IAFL into RA, right? I don't know what is my VA dash. VA dash is not simply 440 because there is some drop happening in this R external. So I cannot simply write this equation. Okay, now I will move on to the third case. So in the third case, they are telling me that they are not changing the armature voltage. So armature voltage and field voltages remain unchanged. So armature voltage is unchanged, that means it is still VA dash. Somehow I am changing my R external, it is still VA dash only. My speed has changed, right? Speed has changed to 1050 and the torque has halved. So why, you might have a question, sir, why is the current halved? Because in case of shunt machine, we have discussed this multiple times, that torque is proportional to flux into IA. Torque is proportional to flux into IA. So what I can say is that as the flux is constant for a shunt machine, flux will be constant. So if the flux is constant, so torque will directly be proportional to the I, right? So if they are saying that torque is half, that means the current is half. So previously if it was operating at full load, now the current will be half of the full load. So the current has been half now. It is IAFL divided by 2. Okay. Now what are they telling is that they are telling that speed has become EB, no load speed, or sorry, not the no load, sorry, speed has become 1050. If torque is halved, the EB dash has become 1050. So from, so not 1050, sorry, NB dash, right? N dash dash has become 1050. So now can you find out the EB dash? EB dash will be what? EB double dash will be simply equals to, again the same thing, right? Previously it was 220 into the new speed upon the old speed. So just it is proportional to the speed, right? So this will be 231. 231. So EB dash is not 231. Is this the drop across the armature voltage? No. They are asking the armature voltage drop. Basically, they are asking this value. Armature voltage drop is this. What is the drop across the armature? What is the drop across the whole armature? Which includes the armature resistance as well. So they are asking what is VA dash. That is what they are asking. So again, if I equate this value, so my EB double dash will be VA dash, because the armature voltage drop has not changed, minus the current across the armature into the resistance of the armature. Current has now halved, so it is IAFL by 2, right? So this will be IAFL by 2 into RA. Now my VA dash I can get from here is 231 plus IAFL by 2 into RA. So from here I can simply equate these two equations, right? So here also I can see that my VA dash is equals to EB, that is 220 plus IAFL into RA. So 220 plus IAFL into RA, and this will be equated. So VA dash equals to VA dash. So basically if I equate this equation 1 and equation 2, so this will be 220 plus IAFL into RA equals to 231 plus IFL into RA divided by 2. So from here I can directly say this will be IFL by 2 equals to 11. So IFL into RA comes out to be 22. So from here I can directly find out what is my VA dash. So my VA dash, or the armature voltage drop, will be 220 plus IAFL RA, that is 22. So it becomes 242 volts. Okay, so this is the answer basically. This is the answer basically. Okay, so yeah, this will be the answer for this question. So let's now move on to the next question. This question was actually pretty good, and I hope now finally the armature voltage control is totally clear to you. Okay, so yeah, let's now move on to the next question. So this is the next question where we have a DC shunt motor that runs at 1200 rpm when supplied to 220 volts. So N is 1200 rpm when supplied by a 220 volt DC. Assuming negligible losses, no magnetic saturation, determine its speed supply at if the supply voltage is reduced to 175 volts. So, like one important factor note, we are changing the terminal voltage. So, if they have not mentioned anything about the load. So, if I show you the circuit diagram of a DC shunt motor. So, if I am reducing the terminal voltage, so the voltage across the shunt field also be changed, right? So, the shunt flux will not be constant anymore. So, that also will be reduced. Okay. So, the important portion is that what is my speed proportional to. So speed basically is proportional to EB upon flux, right? So what I can say is that EB is what? EB is equals to VT minus IARA. Here, right, they have not mentioned anything about the load. So unfortunately I have to neglect this and assume this to be very small. Assume very small, because they have not mentioned anything about the load and the armature resistance. So basically roughly I can say it will be proportional to Vt upon 5 for this case. Now one more thing, I say flux is proportional to what? Flux is proportional to the current, field current, that is proportional to voltage upon voltage of the terminal divided by the shunt resistance. So ultimately your flux also is proportional to terminal voltage only. So ultimately my speed is constant. Okay, it is a constant value. So it does not matter whether if I change the terminal voltage or not, the speed will remain same as the previous one. So speed will remain same. In this case, if I assume the load current to be very small. So the key point, the speed will be same if the speed basically will be independent independent of the terminal voltage. In this case, why it will be independent of the terminal voltage? If I assume IA, RA drop to be negligible. Okay, so answer will be N will be equals to N dash will be equals to 1200 rpm. It will not change. it will not change. This will be the answer, 1200 rpm. Okay, now let's do the second question, next question. So next question is this one, where a 200 volt DC shunt motor takes a current of 22 amperes uh, at rated voltage. So shunt motor takes a current of 22 amperes. So this current is the line current because it is showing from the supply. So it's a 200 volts. So Vt is 200 volts and your line current is 22 amperes, operates at a speed of 1000 rpm. The field resistance Rf or RSH is 100 ohms. The armature resistance Ra is 0.2 ohms. Determine the value of extra resistance that must be inserted in the armature circuit to reduce the speed of 800 rpm under the following conditions. So determine the extra resistance so that I can reduce n dash should be equals to 800 rpm. What will be the external resistance value or external? Okay, under the following conditions. First case is when the load torque remains constant and does not depend on speed. So load torque is remaining constant. In the first case, they are telling me that load torque will be constant, TL is constant, independent of speed. That means what? What is torque proportional to? Torque is proportional to phi into Ia. In case of a shunt machine, phi is anyways constant, so torque is proportional to Ia. So I can say the load torque is constant. That means the current Ia will be constant. Ia will not change, right? So in this case, in the first case, what is the Ia? So in the case 1, right, what is the Ia? So if I write down what will be the Ia, Ia will be equals to IL minus ISH, the shunt current. So IL will be 22 amperes minus ISH. ISH is the voltage across the terminals divided by the shunt resistance 100. So this will be basically 20 amperes will be the armature current. This will be equals to the new armature current. This will be same. So basically my EB has to reduce. I have to reduce my EB, right? I have to change my EB because with external resistance, this is the diagram, right? With external resistance. So ultimately, right, what we have to do is we want our speed to be 800 rpm, right? Flux will not change because the terminal voltage will not change. So basically EB1 divided by EB2 will be N1 divided by N2. N1 is 100,000, N2 is 800. So my EB2 EB2 will be basically EB1, that is EB1 is EB1. What is the EB1? EB1 I don't know, right? I will calculate the EB1. So EB1 will be basically equals to Vt minus IaRa. Initially there was no external resistance connected, so this will be Vt is 200 minus Ia 20 into Ra. Ra is 0.2, so this will be 196 volts. Okay, so this will be basically EB2 will be 196 into 800 divided by 1000 rpm. So this will be basically 4 divided by 5 into 196, so 156.8 volts is the EB2. Okay, this will be equals to what? Vt minus IA into RA plus R external, that is the additional external resistance that I will connect, so that the voltage drops further. So this will be equals to, so basically I know RA is 0.2 plus R external equals to VT minus VT is 200, right? 200. So this is 43.2, and IA, right, will not change. IA will be 20 amperes only, 20. So from here I can easily find out what will be the external resistance. So this divided by 20 minus 0.2 is 1.96. So the external resistance that I need to connect is 1.96 in the first case. So what about the second case? What is the condition for the second case? So in the second case they are telling me that load torque varies linearly with speed. So basically what will happen to the load torque? So load torque, they're telling me it varies linearly with speed. So T2 upon T1 will be equals to N2 upon N1. And also I know load torque varies, developed torque varies linearly with current. So basically it will be equals to I2, because flux is constant, I2 upon I1, IA2 upon IA1. So and so basically what will be the current in the second case? IA2 is equals to N2, that is the new speed, 800 upon 1000 into IA1. IA1 initially the current was 20 amperes, now the current will be 16 amperes. So 8.8 into 20 is equals to 16 amperes. So in this case, what will be the like external resistance? So in this case, right, speed has been reduced. So because speed is proportional to flux into current. So yeah, in this case also EB2 will be this only. EB2 will be this only, right? Like this equation will be valid. EB2 by EB1 will be equals to N2 by N1, because flux is constant. So EB2 will be same as the previous case, that is 156.8 volts, correct? So yeah, this will be 156 point. So EB2 from here, from this equation I can find out is 156.8 volts. This is equals to the VT minus IARA. So IA, armature current, is this minus IA to RA plus R external. So this, right, is same 43.2 divided by, instead of dividing by 20, it will be 16 amperes. This will be equals to 0.2 plus R external. So okay, this is the last question actually. Okay, we are almost done. So from here I can directly find out what is my R external into, okay, sorry, 16 inverse into 43.2 minus 0.2, 2.5 ohms. So in this case the R external will be 2.5 ohms. Why? EB2 has not changed, but of course the current has changed, armature current, due to the torque varying linearly. So that's why in this case the external resistance that I need to connect will change. Okay, so that's how things vary depending on the load, how the load is. Okay, so this will be the answer in the second case, and this will be the answer in the first case. So that's it basically for the speed control of a DC shunt motor, and from the next lecture onwards we will start for DC series motors, the speed control for DC series motors. Okay, and also we will discuss about braking of DC motors, and only 2 lectures are left for DC machines, and then we will start with induction machines. Thank you for watching, and I will see you in the next lecture. Until then, happy learning.